Welcome to the Deep Dive, where we take your stack of sources, articles, and research, and really just distill the critical intelligence you need to level up your decision making.
And today, we're making a pretty critical leap.
We're moving beyond simply describing data, past the averages and the variances.
Right, we're moving into actively quantifying relationships and, I think most importantly, making verifiable predictions.
This is the difference between knowing what happened last quarter and having a real framework for forecasting what your next move is actually going to yield.
We're talking about the essential tools for that kind of prediction.
Uh,
Correlation and simple linear regression.
And our mission for you today is pretty straightforward. We want to turn these, let's be honest, sometimes intimidating statistical concepts into practical, actionable insights.
We want to answer that fundamental business question. If I change X, what happens to Y?
And by how much? Right, that's the
Yeah,
key.
exactly, by how much?
So let's anchor this with a classic scenario. Imagine you're a strategy manager at a big retailer, say a Starbucks or maybe a large e-commerce company.
And you're in that budget meeting.
Exactly. You're in the budget meeting, and you have to ask, if I commit to spending $10,000 more on advertising next quarter, how much additional revenue can I realistically expect to get back?
That is the ultimate question in data-driven strategy. And to answer it, you really need two tools working together.
Okay, what are they?
First, you need correlation. Think of it as a quick check. Does a relationship even exist? And if it does, how strong is it?
And the second tool.
That's regression. That's the heavy lifter. Regression is what quantifies that relationship, gives you the actual equation to plug in that $10,000 and get a real forecast back.
Okay, so let's unpack this. We have to start with that foundational step, right? Establishing the relationship.
You have to. Before we predict anything, we need to know if advertising even matters for sales.
How do we do that? How do we quantify that association?
We use correlation analysis. It's a statistical measure of the strength and the direction of a linear relationship between two quantitative variables.
And the tool for that is the Pearson correlation coefficient, usually just called R.
That's the one. And the beauty of R is just how intuitive the scale is.
It just goes from -1 to +1.
Exactly. If R is +1, you've got a perfect positive linear relationship. Think of it like a machine. For
Right.
every hour it runs, it produces, say, 10 more units. It's a perfect lockstep.
And on the flip side, if R is -1, that's a perfect negative relationship.
Right. The classic example is product price and quantity demanded. As the price goes up, the quantity people want to buy goes down proportionally.
But the real world is messy. I mean, you're never going to see a perfect one or a -1 in business data, are you?
Almost never. Most data falls somewhere in the middle. And that's really where the interpretation comes in. How strong is it when it's not a perfect score?
So how do we grade it?
Well, we use these standardized bands. If the absolute value of R is between, say, 0.9 and 1.0, we call that very strong.
And what about weaker ones?
If you're between 0.7 and 0.9, it's strong.
Mhm.
But once you dip below 0.5, you're getting into moderate and then weak territory.
And the key is using the absolute value, right? So a negative near 0.9 is just as strong as a positive 0.9.
Precisely. It's just a strong relationship in the opposite direction.
So let's bring this home with a specific example from our sources. There was a scenario tracking monthly ad spending and sales revenue, and the calculated R value, it came out to 0.98.
Yeah, and an R of 0.98 is, it's almost unheard of in real-world data. It's exceptionally high.
So that falls right into very strong.
Squarely. It suggests an exceptionally strong positive linear relationship. And that finding is your green light. It tells the manager, yes, there is a clear, dependable connection here. We should absolutely dig deeper with regression.
So, okay, we have this incredibly strong association. The data is screaming at us that when we advertise, sales jump up almost perfectly in sync.
It seems that way.
So the decision is easy then. We greenlight a huge budget increase. That 0.98 correlation is basically a guarantee of future returns.
Wow, hang on. Stop right there. Because we are standing on the edge of the single most important warning in all of statistics.
I have a feeling I know where this is going.
Before you allocate a single dollar based on that higher value, you have to internalize this. Correlation identifies an association. It does not prove causation.
And confusing the two is the fastest way to make a very expensive mistake.
It absolutely is. And it's an easy trap to fall into because the numbers, They look so definitive.
Let's use the classic examples. They really drive the point home.
Okay, think about the strong, positive correlation between ice cream sales and drowning deaths,
Right. If you just look at the numbers, you'd think we need to ban ice cream to save
which
lives.
is absurd. Of course, the real cause, the confounding variable, is hot weather. Hot weather makes people buy ice cream, and it makes more people go swimming.
Or the one about the number of firefighters at a blaze and the amount of damage. More firefighters seems to correlate with more damage.
Exactly. So should we send fewer firefighters? Of course not. The size of the fire is what's causing both. A bigger fire needs more firefighters and, sadly, causes more damage.
Okay, so let's bring back to our retail example. We have this strong correlation between X advertising and Y sales. What are the logical possibilities we have to investigate before we can claim that one causes the other?
There are three, and you have to rule out the last two. First, X causes Y. This is what we hope is true. The advertising really is driving new sales.
Okay, what's number two?
Y causes X. This is reverse causation. Maybe the company sees a strong sales month and then decides to allocate a bigger ad budget because, hey, they can afford it.
So the success came first and that funded the advertising.
Exactly. The sales cause the ad spend. And the third possibility is that some other factor, Z, is causing both X and Y.
The confounding variable, like the weather and the ice cream example.
Right. Maybe there was a government stimulus check or a big competitor went out of business. That could drive both the company's confidence to spend more on ads and the customer's ability to buy more.
So for a manager listening to this, how do you actually establish causation? What are the steps?
It takes more than just a high right value. You need three pieces of evidence. First is temporal precedence. The cause has to happen before the effect. Did the ad campaign run before the sales spike?
That seems obvious.
You'd be surprised. Second, theoretical plausibility. Does it just make sense? An ad for coffee driving coffee sales is plausible. An ad for coffee driving car sales? Probably not.
And the third.
This is the big one. Elimination of alternative explanations. And honestly, this often requires actual experiments, A/B testing, showing the ad to one group but not another to truly isolate its effect. Correlation is just the starting point for that whole investigation.
Okay, so let's assume we've done our homework, we've established a strong association, we believe X causes Y. Now we get to the core of this deep dive.
Now we get to the fun part.
We move from are they related to how much exactly will sales change if my ad budget changes.
And this is the power of simple linear regression. We're taking our historical data and mathematically fitting the single best fit straight line through all those points.
And that line has a famous and pretty simple equation, E equals A plus BX. Let's ground those terms in our retail example.
Sure. So E, or yay hat, is your predicted value. In this case, our forecast for sales revenue.
And X is our input variable.
Yep, that's your advertising spend. And then the magic is in A and B. Those are the two constants we calculate that define the line. A is the intercept and B is the slope.
Let's focus on B, the slope, because that feels like the really actionable number here. In our example, the calculated slope was about 8.15. What does that 8.15 actually mean to a manager?
The slope, B, is your rate of change. It tells you exactly how much your sales are predicted to change for every 1 unit increase in advertising.
Yep.
So since our data was in thousands of dollars, a slope of 8.15 means
For every extra $1,000 we spend on ads.
we predict sales will increase by about $8,150 on average.
Whoa, let's just pause on that. That's a return on investment of over 700%, a
Yeah.
715% ROI.
It's an incredible number. And while you still have to vet it, it provides overwhelming evidence to justify that spend. It shows you the leverage in your system. That one number, B, is often the most important output you get.
That's the strategic gold. Okay, now what about the other number, A, the intercept? In our calculation, it was about 38.04. How do we explain that in business terms?
The intercept, A, is your baseline. It's the predicted value of your sales if advertising spending were zero.
So our base sales.
Exactly. It means we'd expect sales of about $38,000 even with no active ad campaigns running. That revenue comes from, customer loyalty, brand awareness, referrals. It's what your business is worth without that specific intervention.
So our full prediction equation is sales equals 38.04 plus 8.15 times whatever we spend on advertising.
Now you've got it. Making a prediction is just plug and play.
So if that manager decides to spend, say, $12,000, what's the forecast?
You just plug in 12 for X. So 38.04 plus 8.15 times 12. That comes out to 135.84. So the expected sales revenue is $135,840.
We've gone from just looking at data to guiding strategy with a precise number.
That's the leap.
Okay, but now we have this prediction. The immediate next question from any skeptic in the room is going to be, how good is this model? How reliable is that prediction?
And that's exactly the right question to ask. We assess that reliability using R-squared, which is also called the coefficient of determination.
And R squared is just the square of our correlation coefficient, right?
It's that simple, and it measures the proportion of the total variation in your sales that is successfully explained by the variation in your advertising.
So since our R was 0.98, our R squared is 0.98 squared, which is about 0.96, 96%.
And an R-squared of 96% is phenomenal. It means that 96% of all the ups and downs we see in monthly sales can be directly accounted for by changes in ad spending. It's an extraordinarily good model.
I'm playing the skeptic here, though. If 96% is explained, why do we even care about the other 4%? Can't we just run with this?
But that 4% is critically important. That is your unexplained variance. It's the other stuff.
Like what?
Competitor actions, a sudden change in the economy, seasonality, even just data entry errors. And while 96 is great, we generally consider anything over 0.70 to be a strong model. A real strategist always wants to know what's in that error term. Ignoring it is how you develop blind spots.
Okay, so we have a strong model, but even the best models have. Well, they have rules you can't break. What are the major pitfalls people need to watch out for?
There are 3 big ones, and breaking any of them can turn your beautiful forecast into a complete guess.
Let's start with number 1, the linearity assumption.
Simple linear regression assumes the relationship is, well, a straight line. You have to check your scatter plot first. If the data looks like a curve, this is the wrong tool.
What's an example of a curve?
Diminishing returns. With advertising, you might see sales shoot up fast at first, but then they start to level off, right?
Yeah.
You hit market saturation. That's a curve. And you need a more complex model for that.
Okay, pitfall number 2. This feels like the one where people who don't understand the stats really get burned. The dangers of extrapolation.
This is a huge one. It means predicting values far outside the range of your original data. So maybe our data only had ad spending between $5,000 and $10,000.
Predicting at 12,000 like we did seems okay.
It's a modest step. It's probably safe. But using that same equation to predict sales if you suddenly spent $100,000, that's reckless.
Because you can't assume the same relationship holds at those extreme levels.
You can't. It's like trying to predict the top speed of a race car based only on data you collected while it was idling. The underlying rules might change completely. You have to stick close to your original data range.
And the final one, the impact of outliers.
Yes. A single extreme data point, maybe 1 month where you had a massive viral event that had nothing to do with advertising, can completely pull your line out of whack. It can skew your slope and your intercept.
So you just delete it.
No, you investigate it. Was it a typo? Or was it a real unique event you can learn from? You don't just delete outliers, but you have to understand how they can distort your model.
This all sounds like it needs serious statistical software, but I know a lot of our listeners use more accessible tools for a first look. Can you do this kind of thing in, say, Excel?
Oh, absolutely. Excel is fantastic for these practical first-pass insights. There are a couple of really easy ways.
What's the first?
Visualization. Just make a scatter plot of your data. Then you can right-click on the dots, select Add Trend Line, and just check 2 boxes. Display equation on chart and display R-squared value on chart.
And it just pops up.
Instantly. You get your ETH equals a plus backs equation and your quality score right there on the graph.
That is incredibly fast. And what if you need the numbers themselves for a report?
There are simple built-in functions for that. To get the correlation, R, you just use Corel. To get the slope, your B value, you use ACC.
So that's how you find the 8.15, the ROI number.
That's it. And then you use intercept to find your A value, your baseline sales. In just a few minutes, anyone can turn a spreadsheet into a working predictive model as long as they respect those limitations we talked about.
This has been a really powerful deep dive. We went from establishing the strength of a relationship with correlation
To quantifying the actual rate of change with the regression line.
and then assessing our certainty with R squared. But the key takeaways are still those foundational rules, aren't they?
They are. Correlation measures association. Regression allows for prediction. And always remember that core mantra. Correlation does not equal causation.
And if we circle all the way back to the beginning, our model explained 96% of the variance in sales.
It did. But we agreed that the interesting part is often in that leftover 4%, the unexplained stuff, The seasonality, the competitor moves, all of it.
So what does that mean for the manager? Are they done?
It means that while simple linear regression is incredibly powerful, because it is simple, it only uses one predictor variable, it's also fundamentally incomplete for most real-world systems.
Because the world is more complicated than just one thing.
Exactly. If we really want to build a robust model, if we want to squeeze that 4% error down to 2% or 1%, we have to start pretending that only one thing matters.
And this introduces the next logical step for anyone listening to explore on their own.
It does. To account for competition and seasonality at the same time, you have to move beyond simple regression and embrace multiple linear regression. That lets you use several X variables at once to really sharpen your predictions. That's the next level of data-driven strategy.
Food for thought. Thank you for joining us for this deep dive into data-driven prediction. We hope this empowers you to question every assumed causal link in the data you encounter from here on out.